All right, so let's check out the homework. Number 1, person swimming in a pool, 50 meters, and probably somewhere there's a time in here. So 50 meters, we know we've got our distance already. And right here we see if she swims a length, takes 24 seconds. So there's our time. And they give you a little solution here for some of these if you want to check that out. I'm just going to go right to the problem now. It says if our swimmer could cross a 16-kilometer channel, maintaining the same average velocity as the first 50 meters, so in the picture here, how long would that take? Well, we need the average velocity for the first 50 meters, and that's going to be our algebra expression. This is changing x over change in time. So we're changing a distance of 50 over a change of time at 24. And get the calculator. So there is our average velocity. And the overall distance of our channel here, so a new distance that we're going to have here, is 16 kilometers, which is, so there's 1,000 kilometers in a meter. So multiply that by 1,000 to get us into meters. And we have our average velocity and our distance. So we're going to use average velocity again, because that's changing x over change in time. But now we know the average velocity. It's 2.08 for that first 50 meters. That's what we want now for the entire 16 kilometers. And we'll solve for that change in time. And that is in seconds. So let's just see, it does want our answer in hours. So to convert this seconds, we know there's 3,600 seconds in 1 hour. So I'm ultimately going to take this number and divide by 3,600. Get 2.14 hours. And that's question 1. All right, so our next one's got a graph. And it says, find the average velocity from A to B. And I wish we could blow that up, but, well, from A to B is from 0 to 1. So that looks like about a rise of 3. So average velocity. Change in x over change in time. Looks like we're rising about 3 over a time of 1. So our average velocity. Remember, average velocity means taking 2 points and you just connect them with a straight line. That's that secant line that gives you the average. And same question, but from B to C. So now we're going to have C looks like it's at 9. So we're going from 3 to 9. Get us a change in 6. And then our change in time, we're going from 1 to 5. So our change in time is 4. Get us, I wonder if we can just plug that in. Will it take that? It does. and then find the average from A to C. All right? So from A to C, so C looks about 9, so 0 to 9. And then the change in time is 0 to 5. And there is our average velocity. So for the intervals, so what's maybe best here is we just did A to C. And this one was the steepest. We look at our first answer. We went from 3 and 1.5 of B to C. And then 1.8 when we went all the way. So I was connecting these two dots. So if we look at the graph as it keeps going on like this, well, let's say if I pick a dot way over here, well, the average velocity is going to be a less steep slope, meaning it's getting slower. So the average velocity is decreasing if we assume this curve keeps going on like this. So the average velocity will be less than all of these values that we got. All right, so I think I get what they're going with here, since they didn't like that they're using the word velocity here and here for all of them, and now they switch to the word speed. So it looks like they're going for something a little different than I was picturing here, but velocity is what we call the vector, the arrow, which contains a length and a direction. The magnitude, meaning the length of the arrow, this is what is usually called speed. So if this is their interpretation, so I'm not thinking this is the best question, a little bit of ambiguity here, but if this is what they're going for, speed, well, the speed is the velocity values all here. That would be the speed, all these values, because that's what we figured out. We figured out the speed here. We didn't actually figure out the direction. So all these would be equal. I would have to say I don't think this last part is the best question, because I would argue we were technically always figuring out the average speed. Now let's check out the next one. And again, if something quirky happens like that, you can always send me an email and I can easily take care of it. So what do we got? We got our family's taking a trip, lives 100 miles away. So our distance here, 100 miles. The first 60 is driven at 55 miles per hour. So we would just look at our average velocity, which is change in x over change in t. What they're saying here is our average velocity is 55 miles per hour. And we traveled that for 60 miles. But we don't know how much time that took, but we can figure that out. A little over an hour. And then you got stuck for 30 minutes. So that's a half hour. So our first length of our journey, traveled a little over an hour. Now we're getting stuck for a half an hour. So now our total time is 1.59 hours. Now we're unstuck. And in order to make up time, our new average velocity, we have another average. New average velocity is 75. And we have to travel the rest of the distance. So we went 60. Total distance is 100. So we got 40 more miles to go. And we don't know that time, but we can figure it out. So we have the total time then of our journey. So just adding those together. And they want to know what is the magnitude of your average velocity for the whole trip. So magnitude just means the positive value, the absolute value. So we want to know the average velocity for the whole trip. Well, the whole trip was 100 miles, and it took us 2.12 hours. So we averaged about 47 miles per hour. So when we stopped there and took our rest, that was a half hour of just zero velocity. So that brought our average down a lot. Let's check out the next one. So at room temperature, speed of sound, 344. And standard units. And we got a time, 7.5 seconds. How many miles? Oh, we're going to have to do a conversion here. How many miles away was the lightning strike? So we have the average velocity from algebra. We know the average velocity, 344. We're looking for how far away it is, and we have a time of 7.5. So that number in the calculator is meters, since everything here is in standard units. So what I'm going to do is I'm going to pull up Google and just look. I have 2580 meters. And that is 1.6 miles. And if you want to use the internet to a conversion like that, I was going to say a translation, but it's actually a conversion. I don't have a problem with that, just so you know how to do it. So on a test, there'll be specific questions like if you can do a unit conversion. But as far as actually solving a physics type of problem, I like all the information to already be in standard units. So that's how I give my questions on the test, always standard units. So you don't have to waste your time converting. All right, we got all sorts of conversions to do here. How much longer does the trip take on Friday and the others? Well, let's see. We normally drive the freeway between those two cities at an average speed. So we got an average speed, 95. We're in kilometers per hour. And a trip takes 1 hour and 28 minutes. The time is 1 hour plus 28 minutes. On a Friday afternoon, however, heavy traffic slows you down to another average speed, 80. For the same distance. So we don't know the distance, but we can get distance from this one. And the first thing we would need to do, we are in kilometers per hour, but we have hours and minutes here. We do need to change this minutes to hours. So 60 minutes is 1 hour. We ultimately have 1 plus 28 divided by 60. So we have an average velocity, which is change in position over change in time. And we know the change in time is 1.47. So we have this equation to solve. So just multiply that. So 139.3 kilometers. That's our distance. That's the distance they're referencing here then, the same distance. They want to know how much longer does a trip take on Fridays. Well, it's the same distance, our 139.3, but we have a slower average velocity. So let's see how much time it takes to do the slower one at the same distance. So remember, this is delta x over delta t. This is our average velocity there. And then here is our change there. Solving for t then. So, well, I'm running out of room here. I guess I'll write this kind of small. So we're going to have 80. So ultimately our calculator, 139.3 divided by 80. So it takes 1.74 hours on Friday, takes 1.47, little coincidence of numbers just being reversed there. And they get the total difference then, 1.74 minus 1.47. This 27. Oh, and they want it in minutes. Okay. Well, so we have 0.27 hours is the difference. That's how much longer it takes on Fridays. 1 hour, 60 minutes. So we'll have to multiply that by 60 to get 16.2 minutes. So it takes 16 minutes longer on Friday to travel that. Now I notice it says 16.5. It's a rounding error because I am rounding my numbers to 2 decimal places. If you want to keep your numbers, more decimal places, you'll get closer to the exact value here. But good that the computer recognizes there is rounding error, so that's good. Okay, and let me just say this. When I first made this video, I actually started on problem 6 and thought I was starting on problem 1. So this ends this kind of cut, and now begins the video where I thought it started. Let's check out the homework. And starting with the first one in the practice homework 2.1 to 2.4. So we got two cars and they're traveling along. And we have this graph, car 1, car 2. And if we look at car 2, we can see its position is ahead of this one. So I'll call this one car 1 and car 2. And it wants to know at which times do these cars pass each other. So this is a position versus time graph. So as our curve goes up, the car is getting farther away. But then at this point at the top, it stops getting farther away. And now the car starts coming back towards us. While car 1 just keeps driving away. So at point D is where they will meet each other and pass each other. So next one, are the two cars traveling in the same direction when they pass? So again, car 1 is just going away from us forever. She just keeps going up the line. But car 2 goes away from us, stops, and then starts coming back towards us. And at time equals 0, you can, or at this time E, it's at position 0. So they're actually going opposite directions at this point. And so they are not traveling in the same direction. At which of these times does car 1 momentarily stop? So again, looking at the position, how do we know when it momentarily stops? When the car turns around. So that doesn't happen with car 1. Car 1 is just a linear function going straight up. But car 2 has a turning point. If you remember back to math, we have the top of a hill or a bottom of a valley of a function. Call that a turning point. A turning point is where the car stops. So it's going away, stops, and then starts coming back towards us. And so that's at position C, is where car 2 is stopping. So whoops, I actually chose for car 2. Car 2 stops at C, but they are actually asking for car 1. And car 1, I was trying to say, has no turning point. If you look at the math function, car 1 is always going away from us. So car 1, there's actually no place where it's turning around. So here's car 2, the car 2 question. Where does car 2 momentarily stop? And that's going to be at the turning point right here at the top of the function. That's C. And the last part, at which of these times are the cars moving with nearly identical velocity? So these are position functions. And remember, the change in position does give us the velocity. And so that means the slope of these curves. So the slope of these curves gives us velocity. So it's asking us, well, car 1 has this linear slope. About where does car 2 look to have the same slope? And if we look here at A, you see the blue line here. It looks like at this point, it's about parallel with this one. There's slopes. And so at point A, it looks like they're going about the same speed because their position functions here have the same slope there at that point. So A. And they're asking if there's any other positions. If we go up here, looks like at B, this spot right here, we draw kind of a line right there to represent the slope of the curve at this point. That's looking to be about the same as car 1 as well. So I'll go ahead and hit a B. But after we go to the top, the turning point, and the car turns around, Now the slope is always negative, so that will never equal the positive slope for car 1. No, there's a... Oh, I guess I can't... It didn't like B, huh? I don't know. B looks pretty close. But they're not taking it. Either way, a little bit subjective there. But I wouldn't do that too young a test there. I'd make it pretty clear. And just to say again, you know, this is all computer graded. I have no problem fixing things if you just want to send me a quick thing. Let's check out the next one. All right, so we got a spider crawling along. And here's the position function down here. And if we look at this blue line, again, this tells us the position of the spider as it walks away. And it's always walking away. It never turns around. How do we know when it turns around? When the function starts sloping down. That means it's coming back towards us. Its position is decreasing. It's coming back towards us. But there's no turning point here. So we'll just look at the function. The velocity is the slope of the position function. So if we look at this first chunk, it rises 3, has a run of 4. So 3/4 is 0.75. That would be the velocity for this first chunk from 0 to 4. So just looking at our choices, we can see that's only going to be this top left and top right one, A and B. They're the only ones that have a positive 0.75 for that initial time to 4 seconds, 0 to 4. And then from 4 to 10, we see there's another slope. And it's not as steep. So that means the spider was crawling away quickly and then slowed down. And then at time equals 10, it just decided to stop and sit there. So you can see as time goes on, it's just sitting at position 4, which means the spider's just sitting there. So to get this slope, the rise is 1 over a run of 6. So that's going to give us our 0.17. So we have a velocity, a decrease in velocity, and then 0 velocity. And the only one that's representing that is selection A. Here we have 0.75 decreases and then goes to 0. While all the other ones don't do that. The C and D don't even start correctly. B does start correctly, but then it goes to 0, which would mean a flat line here, but we don't see that. We see it still has a slope. So A is our choice there. So what do we got here? Captain John. So now we have some information here. So we just look. He's on his sled, and during his test run, he slowed from this speed with this acceleration. So he slowed from an initial speed. So we're going to start identifying the kinematic variables. We have an initial speed, 282, and it's in meters per second, so we don't need to do any conversion there. And they're giving us an acceleration of minus 201. And again, that's in correct units, so we don't have to do any conversion. Now there's something else here to remember, is that the sled stops. So if you look at the question, it says, how long does it take the sled to stop? Well, the sled stopping means you will have a final velocity of 0. And this is our information. And then they're asking for time. And then we would look at our kinematic equations to see which one could solve this question for us. And that one would be that one there. So we have our final velocity, which is 0. We have our acceleration, t, and our initial velocity. And then we can just solve that algebra there. And, of course, pull out the calculator. Get 1.4, and that's the first one. So, an important thing to remember is a piece of information that's not always given to you as a number is when they say things stop. So very rarely will you hear them say, or problems say, that the final velocity is 0. Usually that's something you have to recognize from the problem. In this case, it says the sled stops. And stopping means then a final velocity of 0. So we get a car traveling east and then reverses its direction over that period. So we have, let's just write down a coordinate system, standard type of coordinate systems. Remember that positive is to the right, negative is to the left. And it's traveling east. So we have an initial velocity, car is traveling east, 20 meters per second. And it reverses its direction over a time of 10 seconds. And now it's traveling, its final velocity is now west. So that's to the left, which means it's going to have a minus sign on it. Remember, the velocity is ultimately a vector. It contains direction. So the minus sign indicates it's moving to the left, and it's moving to the left at minus 20 meters per second. And they want to know, what is this car's average acceleration? So average acceleration is velocity final minus velocity initial, all divided by the total time there. So we got minus 40 over 10 to get us minus 4. And what do we got here? Oh, we don't even need the number. All right. Well, it points to the left because of the minus sign, and that is west. So the car's acceleration points west. So we got an airplane. Has to reach a speed. And let's take a look at what information they're giving us. So notice it says a plane accelerates from rest. So there's the number hidden in there. From rest means its initial velocity is 0. It's starting from rest. So there's that kind of hidden number in the words. And it accelerates at a constant rate of 5 meters per second squared. So we've got our acceleration. And this time we have the distance of a runway. And that is x, 1800. And we'll assume the plane reaches the required takeoff velocity, so right at the end of the runway. So in other words, right as it hits 1800, it will have its desired velocity. And it wants to know the time for takeoff. So we need to know what is time. And we would check out the kinematic equations. And the one that will work for us here is the position one. So we have x, 1800. We have acceleration, 5. Oops, I forgot a squared there. T squared. And then the initial velocity is 0. So we're solving for t squared. So we have 5 halves on the right. We can get rid of that by multiplying both sides by 2/5. And then take the square root. So I'm going to use my calculator. So remember to take the square root of both sides there with the calculator to get t. Check out part B. What is the speed? Final speed. So they want to know, then what is that final velocity it reaches? And we could use our time value. However, if you can get away with not using it, you should try, because it's a rounded number, and when you use rounded numbers, you can get more error in your answer. So let's just check it out. If we could solve without t and get our best answer without having to use any rounded values, and we can by using this kinematic equation. So I would suggest having the kinematic equations listed out for you somewhere so you can look at them, check them out. This is the one that will get us our velocity final. We know the initial velocity started from rest, the acceleration, and its position. And again, we would take the square root. So we got 10 times 1800, throw another 0 on there, take square root. So part C. What's the distance traveled by the plane in the first second? Well, we still got our information here. So maybe I should write, well, I can maybe squeeze in there. So now we want distance traveled in the first second. We still know it started from rest, and they gave us the acceleration. And so we can again figure out our distance with this kinematic equation. And plug our stuff in. So now we're solving for x. We have an acceleration. We have a time. The initial velocity is 0. And so we get 5 halves. What is the distance traveled in the last second before takeoff? All right, so I had to grab this piece of paper again. What was our time there that last time? Our time was 26.8. So we are going to have to use a rounded number here. And it's best to use this then, whatever your calculator had, try to get all those decimal places, because I did round to get 26.8. But They want to know the second before takeoff. So it took 26.8 seconds to take off. So that means we have a new time then of 25.8, because that's 1 second before it finally took off. So now our time would be 1 second before, 25.8. And we still know all this information. Started from rest, had an acceleration, and we want to figure out the distance, which we can use with the same equation again. We have x, this kinematic equation, figuring out distance. We got a, we'd have our time, and it did start from rest, so initial is 0. For our distance. All right, so I didn't quite complete that thought there. This is the distance traveled in 25.8. And remember that the total distance traveled is 1,800. So to get actually the distance traveled in the last second, we can do 1,800 minus, and I think we can actually do this right in the box here. And we can. So I actually just did the subtraction there right in the box, and it worked it out for us to get us our answer. So again, I wanted it in the last second. So the plane traveled an entire runway, 26.8 seconds. Then I figured out the distance for 25.8 seconds. I figured out this distance. And we already knew this distance was 1,800. And so we just had to subtract these two distances then to get what that final answer was. And the last part. What percentage of the takeoff velocity did the plane gain when it reached the midpoint of the runway? So the midpoint, so just looking at our information, we still got initial velocity, we've got our acceleration. The midpoint, though, is half of 1,800. So now we're looking at 900 for our distance. We do need to get the final velocity here, since it's asking for the final velocities, and to compare them from halfway to the takeoff. And to get final velocity here, we can use this kinematic equation and plug our stuff in. And that is final velocity squared. So I'll have to take a square root of 2 times 5 is 10. 900, throw another 0 on there, take square root. And what was our final velocity? So part B, what is the speed at takeoff? We had 134. And halfway is 94.9. So we want to know what percentage is this number of this. So in other words, some percentage times 134 is going to give us our 94.9. And we can solve for that percentage by dividing both sides by 134. And so 71%. So the plane halfway was at 71% of its takeoff velocity. Not quite sure if they want a decimal. Oh, there is a percentage sign here at the end. So we'll write it in percentage form. Otherwise, you would have written that as 0.71. So that's percentage without the percentage sign. All right, so this problem worries me a little bit. I mean, overall, it's a good problem, but all this light blue stuff, what they call a solution, worries me a little bit. I think it's a little bit overly complicated, but let's check out. I'm just going to skip it all. If you want to read that, it's also in your practice problems. So we have a car initially traveling along a stretch of highway at an initial velocity. So that's what I would start with writing down. We have an initial velocity, and it begins to accelerate. And then they give us a final velocity. Then it wants to know how far the car travels. 5 seconds. And, well, it asks that over there, but the actual question's over here. If the car maintains a constant acceleration for 20 seconds, what distance does it travel? All right, so, I mean, that's technically not the homework question, so I don't know what that is. Where our time is actually 20 seconds. And we want the distance traveled. And since we have velocities and acceleration, we could get the distance traveled. We could also get the distance traveled through the position result as well. So either way works. And I just noticed I just wrote this out by memory here, but this is the equation. That's 1/2 at squared plus the initial velocity times time. Plug all that into the calculator. And that's the only question. So this is why this one worries me a little bit. Hopefully that was pretty straightforward. And there's just a lot of stuff here that I think may complicate the straightforwardness of the problem. So here's another one. It's got the same issue with this explanation. But let's just see what we got. So if the acceleration is 3, where is it? 6 seconds. So we have unusually an X initial, so we don't see that too much. I'm just going to put that off to the side. And we have a V initial. So whatever X we solve for, we ultimately would have to add to the initial one, since it's not 0. But whatever X we get from our kinematic equations, we'll just add to this initial position. So it wants to know where is the cyclist. All right, so that is looking for position. And again, we can use the position result and punch it into the calculator. And part B. How fast is he moving? 6 seconds. All right, so we got time. Is 6 seconds again. Well, actually, all the information is the same. They're just asking how fast is he moving now. So all the information is the same. We're just looking for the final velocity now, how fast. And we could get that a couple ways, but the easiest one would probably be the linear. So if we want the final velocity, acceleration is 3. Our time is 6. Initials 15. So we got 18 and 15 to get us 33. And there's part B. So I just want to say again, it's a good, straightforward problem. However, it does kind of get cluttered with the picture here is pretty busy. Got a lot of stuff here. If you noticed, I totally ignored. Also ignored this blue box here. And if you want to check it out, it's up to you. But I do worry that this may make things more confusing. All right, now there is something I want to say here. And the only way I can get around it is using the internet. So I'm not a fan when physics problems have non-SI units. So we have 45 miles per hour here. And then they want the acceleration in standard units of meters per second squared. So I'm not a fan of this because it's just kind of extra unit conversion work. Not something I'll do to you on a test. On a test, if it's a unit question, then that'll be the question, how to change the units. But otherwise, I will always give you information in standard international units. So that's what I would say here. If you're doing the homework and you see 45 miles per hour, just go ahead and use Google and find an equation changer that'll just change from miles per hour to meters per second. So here we go. I just did a quick Google. Miles per hour, meters per second. Didn't quite spell that right, but it's close enough. And so our number is 45 miles per hour. Just going to stick that in there. And so we have a speed of 20.12. And so what do we got? It can reach this speed in 2 seconds. So it can reach this speed. So that's a final velocity in 2 seconds. So we got to have time. It does say starting from rest. So there's that hidden number that the initial velocity is 0. And they want us to find the acceleration. And we can do that with the linear result. And initial 0, so we'll just divide both sides by 2. And 2 decimal places is probably going to be too much, but it should accept it and just make a comment that it wasn't the. Oh, I guess it did take all the decimal places. Well, there you go. Oh no, if you look back here, it did put it down to 10, which is the proper significant figures, but you're not going to get penalized if it's not the correct sig figs. But the program will change it for you in case you're curious on how to represent it with significant figures. Acceleration in feet per second. So, well, at least we don't have to change the time. Just want a change from meters to feet. And I don't know offhand what that is, but I do know there's 100 centimeters in a meter, so that'll cancel out these meters. And there's 2.54 centimeters in an inch, so that cancels out centimeters. And then finally, we got 12 inches in a foot, and that cancels out the inches. And I have to multiply that all out with my calculator. So I got times 100 divided by 2.54, and then divided by 12. And then we get 33 feet per second squared. So find the distance. So back in meters again. So that's good. Still looking at our information. Now they want to know, what is the distance? And we do have our acceleration as well. Another one I haven't used it here actually is I could use this result. So this kinematic equation, you got your list. We could actually use this one here. I haven't used that one yet. So we'd have our V final plus V initial, and the time was 2. And actually these 2's will cancel, and we'll get 20.12. And find the distance in feet. You know, how about if I've got 20 meters, that is 65.6 feet. And that's that one. What do you got? A Beretta model gun. Has a barrel length. So this is in millimeters. So there are 1,000 millimeters in 1 meter. We do need to convert this to meters. And dividing by 3 zeros means we're going to move the decimal place 3 times to get our number in meters. And that's probably going to be our position. The bullet leaves the barrel with a final velocity because you know what the bullet starts with for a velocity if it's just sitting there. So it actually doesn't say anywhere that it's at rest. The bullet starts at rest, but I think that's a safe assumption to make. If the bullet is just sitting in the gun, it starts with an initial velocity of 0, and then you fire it, and then it gains its velocity. And then it wants to know, what is the acceleration of the bullet while it's in the barrel? So they want to know, what is the acceleration here? And then check out the equations. The one that can be used is this one. We'll plug our numbers in. A is what we're solving for. So overall, we'll have this 345 squared divided by 2 times that. So that is a pretty hefty acceleration. And they did put that in scientific notation there. So that's to keep us sig figs. Ultimately, we got 3 here, 3 there. But again, you can just put the full number in. So check out part B. All right, so this one is a little unusual. They want you to express it as a multiple of g, which is a little bit unfortunate since that has to do with free fall, which is what we talk about next. But g is the acceleration due to gravity. It's minus 9.8 if it's going down. Again, this I'll talk about this in the next lecture when we do free fall. So again, unfortunate that g is here. But they want to know, how many g's is this? So when people say how many g's, they are going to take the positive number here. So we have this 468,602, and we want to know how many of these g's are in it. So that means division. So this acceleration is about 17,000 times that of Earth's gravitational pull. When you're standing at the surface. Oh, didn't like that. All right, so I see on my calculator I actually hit a 1 instead of a 4 here. And so if I get a 4 in there, it's actually going to be 47816.5. So even larger, so almost 50,000 times the acceleration you feel at the surface of Earth. So again, a massive acceleration. So there we go. So again, my mistake was just a calculator mistake. I put a 1 here instead of a 4 on my calculator. For how long is the bullet in the barrel? So going back to all our information, now they want us to figure out time. And there's a couple ways we could do this. I'm going to choose this equation again now, since it doesn't get used too much. So we know our distance. We know the final velocity. The initial started from rest, and t is what we're solving for. So that's just going to be that in the calculator. So there's the calculator display right here. And if you did want to write this in scientific notation, usually that means, well, you can put the decimal anywhere you want here, really. But I'm going to choose right here, put a decimal there to make that 7.36. And then that means that I moved it 1, 2, 3, 4. So that would give me times 10 then to the minus 4. So if I put the decimal place right here, then I have to move it 1, 2, 3, 4 to get it right there. Means times 10 to the minus 4. But you know, actually it's probably easier just to type it in with the zeros. And then they went and put it in scientific notation. And there's that one. And that is actually the last one. So there is the practice homework.